Next week, if you already know, we have something called spring break. For some people, it hasn't arrived soon enough. But in any event, the warning I'm giving you is that next week there won't be a colloquium. So if you come over to this room, you will be all by your lonesome. Today I have the pleasure of introducing Peter Pacheco, professor at the University of San Francisco. He's going to bring us up to date on high-performance computing. Let's welcome our speaker.
Thanks, George. So up-to-date may not be entirely accurate, but perhaps more up-to-date on GPGPU programming. So in high-performance computing, so that's the computing that uses the most sophisticated hardware and aims for the highest performance. In high-performance computing, there's been a widespread move from the use of just conventional CPUs like x86 to the use of conventional CPUs and graphics processing units. So those are the processors that draw the beautiful images that you see when you play video games and whatnot. In this talk, I'm going to talk not about graphics processing, but general purpose processing, like sorting, matrix computations on graphics processing units. And that's called general purpose programming on GPUs. I'll try not to say GPGPU because I'm liable to trip over my tongue. Okay, so there's not really a standardization in graphics hardware or APIs for programming graphics hardware. So I'm going to focus on Nvidia GPUs and Nvidia's. Is this something I should worry about? All right.
So you're stuck here for the rest of the day.
Okay. In any case, we'll be talking about Nvidia GPUs and Nvidia's own API for programming these GPUs, CUDA. So let me tell you, before you get your hopes up too high, that it's been almost 10 years. I think in the fall it'll be 10 years since the first CUDA software development kit was released by Nvidia. And in those 10 years, there have been literally thousands and thousands of applications developed using CUDA. And to make things even more complicated, CUDA has changed dramatically. Okay? So I'm going to sort of be talking about a snapshot of the world of Nvidia processors and CUDA that's not absolutely the latest, because I don't have access to absolutely the latest hardware. Okay? Okay, so rather than try to give an overview of all this, I'm just going to look at a couple of simple applications so you'll have some idea of what's involved in this general purpose programming for GPUs. Okay? So we'll start off talking about general GPU programming, and then I'll focus pretty quickly on Nvidia GPUs and CUDA, but the bulk of the talk is going to be focused on a couple of examples. The first is just vector addition, and the second is a dot product. Okay? Okay, so maybe some of us remember that in the 1990s, computer gaming went crazy, and people were very insistent that they needed the absolutely highest resolution graphics for their computer games. Well, the computer industry hasn't been shy about taking on challenges. And one of the challenges they took on was meeting this demand for graphics hardware. And between 1990 and 2000, there was a vast increase in the performance of GPUs, graphics processing units. And we all know that programmers are nerds, and when they see this hardware that's got all this computational power, they have to put it to use. Okay? So in the early 2000s, a bunch of programmers felt that GPUs were so powerful that they wanted to use them for general purpose applications, not just drawing pretty pictures. Okay? And so that was the beginning of general purpose programming for GPUs. And initially, it was pretty challenging because these graphics processors ran graphics APIs like Direct3D and OpenGL. So you wanted to do things like searching and sorting using something that's designed to draw polygons and shade, okay? But they did it, but it didn't take long for a bunch of other APIs to be developed. The first was Brook, which was developed at Stanford, first release in 2003, and then the commercial developers started getting into it. ATI developed an API called Stream. Nvidia developed CUDA. There was an industry group led by Apple that developed OpenCL. And more recently, Nvidia, a software development company up in Portland called the Portland Group, and Cray developed an API called OpenACC. Okay? Right now, ATI has stopped supporting its proprietary API and is supporting the industry standard OpenCL. Nvidia continues to support CUDA and OpenACC, and CUDA is still the most widely used API for GPGPU. It has a very sophisticated development environment, and factors of 10, probably factors of 100 or 1,000 more applications have been coded in CUDA than any of the other GPGPU APIs. Of course, it is only available for Nvidia GPUs, so if you've got an Intel graphics processor or an ATI graphics processor, you probably are going to have to write in OpenCL. Okay. So let's see. I want to talk a little bit about GPUs, and I want to warn you that terminology is not standard. All of the vendors are trying to sell you GPUs, and so they want very exotic terminology, okay? And they don't want it to sound like what the other person has, okay? So since we're talking about NVIDIA, I'll use NVIDIA's terminology in describing their GPUs and in talking about CUDA, okay? Okay, so NVIDIA GPUs are composed of what they call streaming multiprocessors. Used to be SM. The marketing people got hold of it and recently decided SMX was much sexier. So now they're SMXs. I'll probably continue to call them SMs. Anyway, each streaming multiprocessor consists of what CUDA calls cores or thread processors, and there are at least 8, and 8 is actually a much older version of the NVIDIA GPUs. Now there are considerably more of these thread processors. In any case, by a core, they don't mean a core as in a core in your x86 box. They mean a core as in your x86 box, but no control unit, okay? So if you've done Hennessy-Patterson, it's what Hennessy-Patterson calls a data path, okay? okay? But they can't issue their own instructions. They have to get their instructions from somewhere else, okay? So there is a single control unit for all the cores, but it can issue multiple instructions to different cores. In particular, it can issue different instructions to each of the streaming multiprocessors, okay? Now, what I'm going to do in the course of the talk is try to give you, at first, a somewhat imprecise picture of what's going on and try to make the picture more and more accurate as we go along. In other words, I'm going to try not to overwhelm you with too much information. Okay, we'll see how that goes. Okay, so as a first approximation, within a single streaming multiprocessor, the cores operate in SIMD fashion. How many of you have encountered SIMD before? A few, okay. So SIMD is short for single instruction, multiple data. And in SIMD execution, all the cores execute the same instruction as the other cores, or if they can't, they're idle, okay? And the parallelism is obtained through the cores operating on their own data, okay? So let's look at a very simple example here. So suppose we want to find the absolute value of my copy of X. So each of us has a copy of X, okay? And we want to store its absolute value in my Y, okay? Well, we could obviously write that in C or Java something like this, right? Check to see whether it's bigger than or equal to 0. If it is, we put my X and my Y. Otherwise, we put minus my X and my Y, okay? Now, remember, all the cores are executing the same instructions. So we're a bunch of cores. We've got a bunch of copies of my X, and we want to set up our copies of my Y, okay? So at time 0, we all do the test to see whether my X is bigger than or equal to 0, okay? Then at time 1, all the threads with my X bigger than or equal to 0 are going to assign my X to my Y, okay? And all the threads with my X less than 0 are going to be idle. Okay? Then at time 2, we reverse the situation, okay? The threads, that should be my X, the threads with my X less than 0 are going to do the assignment, and the threads with my X bigger than or equal to 0 are going to be idle, okay? Okay, so these conditional branches are a problem with SIMD systems because we essentially use 2 instructions where in a CPU, 1 would do the job, right? Okay, so in Nvidia jargon, that's called thread divergence, okay? The threads running on a streaming multiprocessor are executing different instructions, okay? Now, this is within a streaming multiprocessor. Threads running on different multiprocessors can run different instructions, okay? So if we somehow manage to put all the positive values on our first streaming multiprocessor and all the negative values on our second streaming multiprocessor, presumably we wouldn't have this bad thread divergence, okay? Okay, now what does all this look like? Okay, this is a block diagram of a system with an Nvidia GPU over here and an x86 host over here. Okay, so remember there's this one control unit up here, and it's issuing instructions to each one of these blue streaming multiprocessors. And the little blocks in the blue are the thread processors or cores, okay? Now, each streaming multiprocessor has some local memory or shared memory, okay? And all the streaming multiprocessors have access to global memory or device memory, okay? So the threads in a streaming multiprocessor share that, okay? All the threads share that, okay? Now, an important point here is that the memory that your x86 processor is accessing is different from this device memory. Now, NVIDIA has done a lot to try to hide that, and in more recent versions of CUDA, it's pretty well hidden. But the fact is, you don't directly access device memory from the host. You don't directly access host memory from the device. Okay? At least that's the model we're going to be using. So that's going to complicate things, but just keep that in mind. Okay, so when I ran the applications that we're going to be talking about in a little bit, I ran on a Quadro 600 GPU. Okay, so that's an Nvidia GPU. It's got two multiprocessors. Each of the multiprocessors has 48 cores. The clock speed is about 1.3 gigahertz. Those little shared memory blocks are only 48K, real small. Okay? And the global memory is a gig. Okay? Okay, so this is a kind of not a very impressive NVIDIA processor. The big iron that they have at places like Lawrence Livermore and LBL, okay, they're going to use GPUs more like the Tesla K80. That has about 5,000 cores distributed across more than 25 streaming multiprocessors. Okay, so that gives you some idea of the kind of scale we're talking about for high-end GPUs. Okay, so how do we take advantage of this? All right, the big hardware advantage is there's hardware context switch between the threads that are running on a streaming multiprocessor. So how many of you know about context switching? A few, okay. So you probably understand that your CPU is switching between applications all the time, okay? When it does that, the operating system has to get involved. So there's a lot going on in software when you switch between applications, and that's called a context switch, okay? Okay, well, NVIDIA tries to avoid this problem by doing the context switching in hardware. In other words, if the hardware sees that a core is idle because, say, it's waiting for data, remember transferring data from memory into the core is relatively slow, okay? If it sees something like that, it can almost instantly switch to another thread, okay? So context switching is much, much faster on an Nvidia GPU than it is on something like an x86. Okay? Okay, so that's something that Nvidia has given us. Okay? And we as programmers want to try to avoid thread divergence. Okay? Clearly, that's going to be expensive. It's going to basically double our costs. Okay? And we want to exploit this hardware context switch. And the way we exploit the hardware context switch is we run huge number of threads on streaming multiprocessors. Okay? If I've got a streaming multiprocessor with 48 cores and I put 48 threads on there, when a thread's idled waiting for data from memory, it's idled. Right? That core's lost to us until the data gets there. But if I run, say, 1,000 threads on my streaming multiprocessor, when one of those is idled, okay, we can immediately put in another one that's got its data and do useful computation. Okay? All right. Good. Clear. We got all that. Okay. So CUDA. CUDA was originally an acronym that stood for Compute Unified Device Architecture. And the Compute Unified means that in the CUDA program, you program both the CPU, the x86, and the GPU with your one CUDA program. Okay? Now it's just a marketing acronym. It doesn't stand for anything except their API. Okay? So CUDA source is put in a .cu file, so you're probably familiar with .c or .cpp. Okay? The CUDA suffix is .cu, and it's a modification of C, C++. So CUDA programs look a lot like C, C++. Okay? In fact, you can take pretty much any ordinary C program and lots of C++ programs, compile them with a CUDA compiler and run them, but they'll make no use of the GPU. They'll just run on the CPU. Okay? Okay. One point that's worth mentioning is that CUDA, unlike many other APIs for parallel computing, is not a library. Okay? We need to modify the compiler to make CUDA work. Okay? Okay. So CUDA programs like C, C++ start in a main function that runs on the CPU or host. Okay? And the main function runs in essentially the same way that an ordinary C, C++ function would, okay, with the exception, the important exception, that there are these special functions called kernels. Okay? A kernel is a CUDA function that's called by the program running on the CPU or host, okay, but it actually executes on the GPU or device. Okay? So when you talk to Nvidia nerds, host x86, device GPU. Okay? Okay. And they're typically quite small. You'll see, we'll write several of them today, and you'll see that they're only a few lines long. Okay? Okay. So let's start writing one. All right, so I want to do vector addition. Okay? And you don't have to think that this is vector addition if you don't like linear algebra. You can just think of it as doing some strange things with arrays. Okay? So I've got two input arrays of floats, okay, and an output array of floats, and an int telling me how many elements are in these arrays, okay? And then I just iterate through the arrays, adding xi to yi and storing the result in zi. Couldn't be simpler, right? Everybody understands what this code is doing? Yes. Okay, good. Okay, so, so if we put the source up there, I toyed with doing that and decided ultimately that it would probably be intimidating, okay, because of all the funny notation. But if we put the source up there and you're familiar with C, you would say, oh, this is a C program, okay? So you include your favorite header file, standard IO, standard lib, and math. Okay? And the only difference between your C main function in this vecadd program and an ordinary C function is going to be the call to this kernel. Okay? Okay, so what do? Well, remember that we've got separate memory on the device and separate memory on the host. So anytime we want to allocate memory on the host, we usually need to allocate it on the device and vice versa. Okay? So I'm going to have arrays x, y, and z on my host and arrays x, y, and z on the device. Okay? The reason for that is the device isn't really good at I/O, whereas the host is. So if I want to read this stuff in, I should probably read it in on the host. And if I want to print it out, I should print it out on the host instead of the device. Okay? Okay, so I'll initialize x and y on the host, and then I'll copy these guys to the device using a CUDA library function called CUDA memcopy. Okay? I'll use malloc to allocate the storage on the host, and CUDA malloc to allocate the storage on the device. Okay? Okay, so our picture is going to look something like this. We've got our host arrays, which we initialize, and then we'll send them over here to our device arrays using CUDA memcopy in that direction. And then when we're done computing Z, we'll copy Z back to the host, also using CUDA memcopy. Okay? Okay, so by analogy with the hardware core and streaming multiprocessors, the software analogs are thread for core and thread block for streaming multiprocessors. So the idea is you run a bunch of threads on a streaming multiprocessor with threads taking the cores. Okay, so at any given time, hopefully you've got a thread running on the core, on each core of your streaming multiprocessor. Okay. Okay, so the next thing that we want to do after setting up our memory is to determine the number of threads per block and the number of blocks. And as I mentioned earlier, we want lots and lots and lots of threads. So we want blocks that are way bigger than the number of cores we have at our disposal. Okay? So in the examples we'll be running today, remember, I've got 48 cores, okay, in my streaming multiprocessors, and I'm going to be running 512 threads on that. Okay. Generally speaking, you want more blocks than streaming multiprocessors, but there is a downside to that in that you remember that little shared memory block? Each streaming multiprocessor had a little piece of shared memory. That's tiny, and you can really limit the amount of storage you've got if you're running multiple thread blocks on a single multiprocessor. As we'll see, that's not going to be an issue for us. Okay? Okay. All right, now the call to the kernel, and this is where you're not in C anymore, you're in CUDA. Okay? So the name of our function is vecadd, the name of our kernel is vecadd, so just as we would in a C function call, we put that at the beginning. And then we list our arguments to the function. Okay? But between the name of the function and the argument list, we've got this goofy stuff in angle brackets. And what we're doing in the triple angle brackets is we're telling the CUDA runtime system how many blocks we want and how many threads do we want in each block. Okay? Okay, so another thing to notice here is that these are addresses that were returned by our calls to CUDA malloc. Okay? What's going on here? Well, we've got a block of memory on the host, we've got a block of memory on the device. The addresses on the host mean nothing on the device and vice versa. Okay? So these are addresses on the device that were returned by our call to CUDA malloc. Okay? If we tried using host addresses, no telling what would happen. Okay? We might get a segmentation violation. We probably just would get garbage as our output because the addresses on the host are meaningless. In other words, if I did hx, hy, hz here, no telling what would happen. Now, these arguments are passed by value. So this address is passed over, this address is passed over, this address is passed over, and the value of n, the number of elements in our arrays, is also passed over. Okay, now, at this point, we don't know what's happening on the device. Remember, this is code running on the host. Okay? We don't know whether the device has finished adding these guys together and putting the result in Z. Okay? How do we find out? We call this CUDA thread synchronized function, which is going to wait, okay, until all the threads running on the device are done. Okay? So this is to ensure us that we don't start trying to use Z before it's ready. Okay? Okay, let's see, I think we already talked about that stuff. Okay. Okay, we've returned from our call to the kernel, so what do we want to do? We want to copy the result, the sum vector, back to the host, print it out, free up our memory. We'll just use free on the host, CUDA free on the device, and quit. Okay? Okay, questions? That's either good or terrible. Okay. Okay, let's look at the kernel. The kernel is identified by this keyword underscore underscore global underscore underscore. Okay? Kernels don't return anything to the host, so the return type is always void. Okay? Arguments, we already talked about. Okay? And so let's look at the code. When the kernel is started, the CUDA runtime system is going to take the information we have about the number of blocks, okay, and the number of threads in a block, and store them in these structs. Okay? So what I'm doing is taking these CUDA-defined structs and getting the number of threads per block, okay, which block I happen to be in, and which thread I am within that particular block that I belong to. Then I can get a global index into my arrays X, Y, and Z by multiplying the number of threads per block by which block I'm in and adding in my thread. We'll look at that in more detail in a second. Then basically we do the addition. Okay? So the idea here is we're running one thread per element of these arrays. So think millions of elements in these arrays, millions of threads. Okay? Okay, now, for reasons that'll become clear in a little while, it's not unusual to do things like make threads per block a power of 2. Okay? And your array size is probably determined by the application. Okay? So you may actually need to have more threads started than you've got elements in your array. So it's quite common to see tests like this in CUDA kernels, checking to make sure this index is actually corresponds to a legitimate element here, not a thread that was started because of restrictions on the sizes of thread blocks. Okay? Okay, so let's come back, let's talk a little bit about that. Okay? So suppose we've got 2 blocks of 4 threads. Now this is a tiny example, but it's an example that I can manage. Okay? And we've got 6 elements in our arrays X, Y, and Z. Okay? Then the number of threads per blocks is going to be 4. Okay? The block indexes, we've got 2 blocks. So the block indexes are going to be 0 and 1. And the thread indexes in each of the blocks are going to be 0, 1, 2, and 3. Okay? Just like C Java arrays. Okay? So over here in my first block, that calculation I was doing is going to multiply the number of threads per block by this. So I is just going to be 0, 1, 2, and 3 in that first block. Okay. Then in the second block, we're going to be multiplying our 4 by 1. So we'll be adding the index within the block to 4. So we'll get I, 4, 5, 6, and 7. Okay. And then, since n is 6, we'll cut off here. These 2 threads are going to do nothing. And those 6 threads will do the vector addition. Okay? Okay. Let's see. So I've already mentioned that the kernel has return type void. so it can't return anything. And I see I'm running way out of time here. Okay, so we're going to have to rush. You also can't do things like pass by reference. Okay, and that's the same reason that we were talking about before, that the addresses on the device, okay, are different from the addresses on the host, and that's what you use to do pass by reference. So the only way to get results back to the host is to do that mem copy, CUDA mem copy. Okay. Okay. So real quickly here. So I ran the code this morning with 2 to the 20th as n, 2 to the 11th as the block count, and 2 to the 9th as the number of threads per block. And my Xeon 2.4 gigahertz, took about 5 milliseconds, okay? Whereas this took about 0.8 milliseconds. So it's almost 6 times faster, the CUDA code, than the serial code. Okay? Now, unfortunately, I cheated. I didn't cheat in the sense that this doesn't work. What I did was I used an extremely simple application where all the threads are operating independently of each other. Okay? I work on my xi, my yi, my zi, you work on yours, and we never need to talk to each other. So this application is what's called embarrassingly parallel. Okay? It's impossible to screw it up. Okay? Okay, so let's, golly Moses. How did it go away so fast? Okay, so let's talk about the problems that can arise. We know that there is this little block of shared memory on each streaming multiprocessor, and there's this big block of global memory shared among the threads. And this is where we can start stepping on each other's toes. Okay, so let's look at a quick example here. How many of you are familiar with race conditions? Oh, good. Forget this example. Okay, so here we've got shared X, okay, private Y, okay. The updates to X form a race condition, okay. It's going to sort of depend on who gets there first, okay. So if we start off with X equal to 2, we start off with Y equal to 3 here and 5 here in these private variables, and we can get 2 plus 3 plus 5, 10. We can also get 2 plus 3, or 5, or we can get 2 plus 5, or 7. So we got a problem here, okay? So this is a sort of a form of a race condition called a non-atomic operation, okay? So what happens when we do this addition is actually involves multiple steps on most systems, and those steps can overlap and tread on each other's toes, okay? So let's just look at that. So the addition might involve a couple of loads, so that's transfer from memory to registers in the processor, an add, and then a store. Okay. So if thread A starts at time 0 and does these steps, it'll be done at time 3. Okay. Thread B is still computing. Okay. What happens here? We're going to load X. We haven't gotten the updated X, so we're going to load X equals 2 into our register. Remember, the threads have their own registers. Okay. So when we load 5 in and do the adds, we're going to be adding 5 to 2 here instead of 5 to 5. Okay? So we're going to overwrite the 5 that was computed here with the 7 that we just computed. Okay? Okay, that's a problem, right? Okay. All right, so what I want to do in my remaining 5 minutes is look at a couple of CUDA kernels that try to do a dot product. Okay? So in a dot product, we've got our two arrays. We're going to multiply instead of add, okay? But we're going to compute a single number as output, okay? We're going to add these products together, okay? So I'll do x0 times y0 plus x1 times y1, and so on and so forth. So obviously the issue is the addition into dot, okay? Okay. So CUDA has these things called atomic functions, and there's this thing called atomic add. Basically, if you do your addition inside the atomic add, it's going to guarantee that no other thread steps on your toes. Okay? Your work isn't going to get overwritten. Basically, what happens is your addition is going to start and complete before anybody else's can start. Okay? Okay. So what our kernel is going to look like is same setup as before. We get this global index. Okay? Then we compute x sub I times y sub I, and then we use this atomic add function to add our calculation into the total. Since addition's commutative, we're going to get more or less the same answer every time. For those of you that are into numerical analysis, you can pretend you didn't hear me say that. Okay, so let's look at the performance of this. Same size arrays as before, same serial processor, and whoops, 4 milliseconds, 20 milliseconds. Bad, bad, very bad, right? We just wasted a lot of time making our program run slower. Okay? Okay. It isn't surprising because what does atomic add do? It serializes the access to the dot product, right? To that sum variable. Okay? So one thread does his addition, another thread does her addition, another thread does hers, and so on and so forth. So you expect that to stink. Okay, well, we've still got 2 minutes. Okay, so suppose we had 8 students. Each of them sat down and calculated a number, and we wanted to add them all up. How would we do that? Well, we could give them all to me and make me add them up. Right? But I think we can probably agree that that would not be the most efficient way to go about doing this. Okay? Okay, so what we want to do is try to use the fact that we've got 8 people that know how to add, okay, and get them working together to do the sum, so we can do something like this, okay? So we've got students 0 through 7. They've each computed a number, okay? And in this particular setting, okay, my odd-ranked students are giving their results to the even-ranked students that they're next to. The even-ranked students will take the values that they get and do the addition, okay? Then we'll throw out the odd students. They get to go home. We're just left with the even students. Now the ones that are divisible by 2 but not 4 are going to send to those that are divisible by 4, okay? Divisible by 4 does the addition. Okay. Then divisible by 2, not 4, drops out. And then finally, 4 sends to 0. 0 does the final addition. Okay. I don't guarantee the arithmetic is correct, but the principle is. Okay. Okay. Well, we can do the same thing in shared memory. Okay. We don't have to send things. So let's take a look at what happens, okay? So now I'm going to put each thread's calculation into this shared array, okay? And so thread 0 calculated 2, thread 1 calculated -1, and so on and so forth, okay? And to do this, threads 1, 3, 5, and 7 are going to do nothing. 0 is going to grab the value in 1. 2 is going to grab the value in 3. 4 is going to grab the value in 5. 6 is going to grab the value in 7 and add. Okay. Then 2 and 6 are going to drop out, and we'll repeat the process. Okay. Then to finish off, 4 will drop out. 0 will get the value in 4 and do the addition. Okay? Okay, so our kernel should do something like this. Okay? So we compute x sub I times y sub I. And then we iterate. Okay? First we do stuff that's only 1 unit away. Then we do stuff that's 2 units away, and so on and so forth. Okay? Now, we've got a couple of race conditions here. Going from here to here, temp sub I may not be computed when we do our first iteration. Temp sub I may not be computed when we do our next iteration. So what we want to do is we want to put a barrier here and a barrier here, okay, so that no thread can start this until all the threads have finished, and no threads can go on to the next iteration until all the threads have finished the current iteration. Okay? So that's going to give us something like this for our kernel. Now there's more going on here, but we're out of time, so take my word for it. It's okay. Okay? I'll put the code online this weekend, and you can look at it if you doubt me. Okay? All right, so let's take a look at the performance of this. Okay? Well, we beat the atomic add, but we barely beat the serial. Okay? All right. Well, sort of to finish off, what's going on here is we've been ignoring thread divergence. And it turns out that communication pattern that I looked at is terrible for thread divergence. Okay? A much better communication pattern gets the distant stuff first and the nearer stuff later. Okay? Okay, there's all kinds of stuff that I'm having to leave out here, but anyway. So basically we're starting with things that are far away and getting closer and closer. And that, it turns out, is going to really reduce the amount of thread divergence that we get. Big win. All right? Now we've beat the pants off of this, okay? And we're twice as fast as those guys. Okay? Okay. Well, there was one other optimization I was going to do, but George has been warning me that I need to shut up. Okay? So let me just say thanks to George and the computer science department here for inviting me. Thanks to Karen Parrish for preparing the diagrams. I'll put this stuff up here this weekend, so if you want to download it, I'll put the talk up so you can get the grubby details I left out. And let me close by asking for questions. No questions. Yes?
How do you know how many threads you should use?
You don't. Okay. So I gave a rule of thumb, which is lots, which isn't very helpful. Okay. So the applications that I was running here, I ran with 2,048 thread blocks and 512 threads per block. Okay. It turned out I tried running them with 1,024 thread blocks and 1,024 threads per block, and it really killed the performance. Okay. So the way you really know is you experiment. Okay. Other questions? Yeah.
So if you have, say if you have an Nvidia GPU, is this something that you can just do on your machine anytime, like writing a C++ or C function?
You need to download their software development kit. So you have to sign some sort of agreement saying that your firstborn child will never use any GPU except NVIDIA, okay? And then you can download the CUDA software development kit. And yeah, you can develop applications just the way you develop C++ applications, okay?
Okay, thank you.